Okay. So just like the Friday we had 2 weeks ago when we took a first quiz, the structure for today's class is going to be pretty much the exact same. In that the first 10 to 15 minutes, I'm just going to go through maybe like a problem or more from the notes this week. The next 15 minutes, there'll be a practice quiz, and then whatever time remains in the rest of the class, you'll have the actual quiz. So I kind of like the practice quiz idea. I think you guys like it too. So I'm just going to try and utilize it when possible. And so again, as a reminder, I sent an email about this yesterday, but the quiz is going to go over sections 1.4 and 1.5, which is what the homework covered, not like section 1.7 and 1.8. I wanted to make it so like when you're doing the homework, you're studying for the quiz instead of having to like do the homework and then study for the quiz after doing the homework, which is it'd kind of be a lot, in my opinion. Yeah, so over the next 10 minutes, I'm just going to go through maybe like another example from the notes this week, maybe two examples. The example I wanted to focus on is the last example on the notes. So it's this additional example. This one's a little bit different from the other examples that we went through this week. It's kind of like a direct proof, but like backwards, but it's not the converse and it's not the contraposition. It's a little bit weird, but by going through it, hopefully you'll understand it. So for this example, it asks for distinct positive real numbers x and y. It wants you to prove that the arithmetic mean x plus y over 2 ends up being greater than the geometric mean, which is the square root of x times y. And so before even really getting started with the proof, I would recommend just kind of doing a little bit of work with the like inequality that it wants you to prove. So let's do a little bit of work first. And let's just start off with the identity or the inequality they want us to show. So if x plus y over 2, and we want to show it's greater than the square root of x times y. And so we want to mess with this inequality to the point where eventually we get something we know is going to end up being true. And so we're just going to perform some algebra. So one thing you can do to get started is we don't like square roots usually. So one thing you can do to get started is take the square of both sides. So if you take the square of both sides, this is the same thing as saying x plus y squared over 4 is greater than x times y. We don't like having denominators, so we can multiply everything by 4. So if we multiply everything by 4, this inequality holds if and only if we have that x plus y squared is greater than 4 times x times y. And then instead of having like, there isn't much we can do with just like the x plus y squared as it is. So it's a good idea to expand things. So that way we can make things easier to kind of visualize or see. So if you factor this or FOIL this out, this is going to be x squared plus 2 times x times y plus y squared is greater than 4 times x times y. And we just keep on going. Okay, so we're going to keep on doing more and more algebra. One thing we can do is we have a 2xy here and a 4x times y on the right-hand side. So maybe we can do some sort of subtraction. So this is going to be x squared. So if we subtract both sides by 4x times y, this will give you a minus 2x times y plus y squared. And then this is all going to be greater than 0.
Is that a 2 or a z?
It's a 2. Yeah, because I mean, if you do 2 minus 4, like you get a minus 2. Okay, and then from here, we're almost done at this point, right? Maybe I'll ask you, does anyone see a way in which we can rewrite this in a way that's a little bit easier to understand? Yeah, go ahead.
X minus y squared.
Yeah, so this is the same thing as having x minus y squared is greater than 0. And then does anyone see, like, what's the significance of this? Like, what can we say about this statement? Yeah, in the back.
On long as x y to c reverse there's the difference of what are the differences of all of these?
Yeah, exactly. So we said in the beginning that x and y are distinct numbers. So as long as these two numbers are different, we're going to get a number that's not equal to 0. And then when we square it, you're always going to get a number that's greater than 0, right? So the main observation is that, so you can say something like, as x minus y squared is greater than 0, whenever we have that x is not equal to y. Remember, like when we were going through these steps, all these arrows are biconditional, like they're if and only if, right? So we were able to show that this x plus y over 2 is greater than the square root of xy holds if and only if this holds. And we know that this always holds. So it has to be that the initial step or the initial inequality always holds as well, right? So as x minus y squared is greater than 0, whenever x is not equal to y, it follows that we have that x plus y over 2 is greater than x times y. So sometimes, I mean, we didn't really have to do that much work algebraically in the previous examples, but for some examples, like you do have to kind of start off with the inequality and then see like what you can do with it via algebra. And maybe things will work out, maybe things won't work out, and you have to try another method. But in this example, it ended up working out, right? And it's worth noting when you perform these algebraic steps, these are all like equivalences, right? These are all like biconditional. So if like you multiply things by, if you like square both sides, like it's gonna have an if and only if. If you multiply both sides by 4, it's gonna be if and only if, so on and so forth, right? Because you can always undo the step and get back to where you originally were.
Of course, this assumes that there's x plus y would need to, or both need to be positive in order for x, y to not involve in imaginary numbers.
Yeah, I mean, it says here, like we're assuming that x and y are both positive numbers in the beginning. Okay, any other questions about this example? Let's see. It's 8:07. I think I have time to go through one more example before the practice quiz. Let's go through this existence proof. It's a little bit interesting, I suppose. So we went through an existence proof in class on Wednesday when we did this like uniqueness. So like the first part was showing existence, the next was showing uniqueness. This one's a little bit different. And that for this example, it wants you to show that there exist irrational numbers x and y, such that x to the y power ends up being rational. And so, I mean, in class on Wednesday, we showed that the square root of 2 was an irrational number via contradiction. So let's just see what happens if we consider x is equal to the square root of 2 and y is equal to the square root of 2. Oops.
So they don't have to be distinct?
No, there's no, yeah, it doesn't say anything about x and y being distinct from one another. And so what we want to look at is we want to take into consideration x to the y power, which is equal to the square root of 2 to the square root of 2. And just by looking at this, I mean, we don't really know whether or not this is going to be rational or irrational. I know for a fact that this ends up being an irrational number. But say like we don't know whether or not this is going to be rational or irrational. We can say is either rational or it's irrational. And so the main point is, if we know that this is going to be a rational number and irrational, I'm sorry, if we know that this is a rational number, then we're done, right? Because we wanted to find two irrational numbers such that if you raise one to the other, it's going to be rational. So we can say something like if the square root of 2 to the square root of 2 power is rational, then we're done. Otherwise, it's irrational and we have to keep on going. So it's irrational. And I would just use the words. So I would say like, so we keep on trying or something like that. Right, so there's like kind of two cases. This is either rational or irrational. If it's rational, we're done with the problem. If it's irrational, we have to like keep trying to find a number. Such that if you raise x to the y power, it ends up being rational. And so now we're going to suppose, maybe I should do like a new line here. So we're going to suppose the square root of 2 to the square root of 2 is irrational. And now we're going to let x be equal to the square root of 2 to the square root of 2 power. And we're going to let y be equal to the square root of 2. And so now if we do x to the y power, this is going to be equal to the square root of 2 to the square root of 2 power to the square root of 2 power. I know there's a lot of square roots of 2's, but it simplifies here. And that now when we perform like this exponent, what?
You wrote x to the 4.
That's x to the y. Okay, and I feel like they're close enough. Yeah, and so this is if you do x to the y power, like you now have the square root of 2, and then what's going to happen is you have the square root of 2 times the square root of 2. So this is going to be equal to the square root of 2 squared, and this is equal to 2. And we know that this is a rational number, right? And so the main observation is we either have that this is rational, or if we do this combination of numbers, it's going to be rational. So no matter what, we ended up finding some pairs x and y such that if you do x to the y power, it's going to be rational. So the main point is we have, or we found, at least one pair of numbers, x and y, pair of irrational numbers. I'm going to abbreviate numbers as this, such that x to the y power ends up being rational. So this is what's called a constructive existence proof, right? Like we wanted to, like it asks for some sort of irrational numbers or two irrational numbers such that this ends up being rational. And we were able to perform some sort of construction from an irrational number we knew about in the past. Yeah.
We suppose still that the square root of 2 in the power of square root of 2 is irrational. We haven't proved that.
That's yeah, that was the point of this part here. Like we were saying that this is either going to be rational, in which case we would be done with the problem, because then we'd have like a rational to the irrational that's rational.
Okay.
So then we'd be done with the problem. Otherwise, it's going to be irrational.
Okay, and are we like if this happens to be the union thing, would we take like this the case of square root of 2 and square root of y, or would we take like, or we would have to like take a over b to prove that it's that the x would be rational, like what we did in the.
It's gonna, I mean, it would depend on the problem, is what I would say. Like I would say on the exam, you can assume that the square root of 2 is going to be irrational, or like a number like the square root of 3 is irrational without doing it. But I mean, it's gonna depend on the problem. Like for this problem, we didn't have to do anything involving like showing it was equal to a over b or anything like that. But there might be other instances where it's easier to show that it's of the form of like, or it's not of the form of like a over b. It's really going to be context dependent, I would say. Does that answer your question?
Yeah.
Okay. Any other questions about this example? Okay, so it's 8:15. I'm going to stop there. So that way you can focus on the practice quiz. I mean, the quiz itself, I don't think it's very long, but I want to make sure everyone has enough time to kind of, I guess, digest what's going to be going on with it before actually taking the quiz.
Right?
Yeah, so for the practice quiz, I mean, you can do whatever you want. That's what I would say. Or maybe you shouldn't like look up answers online, I guess. But yeah, you can talk to other people.